Hello. Now that you have some fundamental understanding of the vibration of particles, now do you have some fundamental understanding of the vibration of particles? You are familiar with this vibration. Now, in nature, these kind of simple harmonic vibrations are rampant. In fact, energy transferred from one place to another. How do we transfer energy from one place to another? It is actually one very, very popular way of doing that is by setting particles into vibration. Now, I want you to watch this simple illustration I have set up for you. Now, here I have constructed a medium. Now, what is this medium? I have a tape, and on which I have stuck some very light straws. Now, if I can set one of them into vibration, all right, I want you to watch and think about it carefully. If I give it a little jerk on this one, this will vibrate up and down. And because each of these is connected by means of the tape, the energy of vibration will get handed over from particle to particle. I'm going to call each of them a particle. Now watch carefully how they vibrate if I set the first one into vibration. Now, there you are. Do they all vibrate at the same time? No. Now, what's the difference there? If this one starts vibrating, the next one starts vibrating a little later. The energy gets to each of these particles a little later, and as a result, each will vibrate. I'm going to develop this word, you've got to understand that. Each will vibrate in a different phase. Now, look at that. Each will vibrate in a different phase. Another illustration of energy transfer through a medium. I have now here a stretched spring. I suppose you can see that. Each segment of a spring is actually a particle. I can set one particle into vibration. Tell me what happens if I pluck, I'm going to pluck this upward and leave it. Watch what happens. Can you watch what is happening? The energy that I used to pluck it up and down, transferred all the way to the other end of the spring, gets back and forth. The energy travels through the medium, and you can see it takes time for each particle to get energy from the nearest particle. This brings us to an important phenomenon in nature called wave motion. What is wave motion? Well, let's look at a couple more examples. If you tie one end of a rope to a support, stretch it by pulling it on the free end, and give it a sudden jerk upward, well, just like I did it on the spring. Now, this is what will happen. The sudden jerk will set the particles of the rope into up and down vibration, and that energy of vibration gets handed over from segment to segment until it reaches the other end of the rope. Then that energy gets reflected back. Now, this is another illustration of the same phenomenon. You can see a pulse that I generate here. The pulse will move gradually to the right. Well, it happens actually very quickly because the energy, the elastic force binding the particles together are very strong. So you see a pulse moving along the rope. When the pulse reaches the support, it gets reflected back, and you can see how energy travels back and forth through the medium of the spring or through the medium of the rope. So the jerk, the energy of the jerk set the segments into simple harmonic vibration, up and down vibration, and the energy of vibration gets handed over from particle to particle. The energy of the jerk gets passed on from segment to segment due to the elastic properties of the string. You see that? It's the elastic properties that binds the particles together. Now, remember, the rope segments do not move away from their positions. The rope segments simply vibrate up and down like this particle. You see that? Each segment executes simple harmonic vibrations just like the simple harmonic vibrations of the spring, and the energy gets transferred along the medium. Okay, the energy of vibration travels along the length of the rope. Each segment of the rope is set into vibration a little later than the previous segment. Do you understand why each segment starts vibrating a little later than the previous one? That is an important concept. All right. Now, you can see here the vibration of the spring, and if you create waves in water, have you actually seen how waves in water can be created? If you drop a pebble into a pool of water, you can see the water will keep moving up and down, and that up and down motion of each water particle is transferred from particle to particle. The energy transfers, energy travels along the surface. You can see if you keep an object like this on the surface of water, you can actually see that object does not move away. That object will simply move up and down in simple harmonic motion. Try it next time. Take water in a wide container and drop a pebble into it, and keep a small piece of paper at some point on the surface. You can see that paper will simply move up and down. The energy will go past it, but the water particles are not moving away from their positions. It's very important to understand that. Alright, so when a pebble is dropped into a pond of water, the pebble sets the molecules of water into simple harmonic motion, SHM, just as the oscillations of this loaded spring. As the energy reaches each molecule a little later, you can see the wave profile is created because the energy reaches each particle a little later. When a particle here has vibrated all the way up, a particle here will just begin to vibrate. You see the profile of the wave. We will create the profile as we go on. Each subsequent molecule will be in a slightly different phase of vibration. I want you to understand this. I will develop this in our next couple of slides. Now, it is this progressive phase difference. If you move from particle to particle in a medium, there will be a progressive phase difference. And it is that progressive phase difference that creates that wave profile. So, if you understood anything what I have said so far, we can use all that concept to define wave motion. What is the definition for wave motion? We can say wave motion is a kind of energy transfer in a medium. The medium may be water, it may be the straws with the tape, it may be the spring, it may be air, you see? So energy transfer in a medium due to the vibrations of the particles of the medium, with the particles themselves, without the particles themselves moving away. You see, each particle will simply vibrate up and down. This particle will not move away from its positions. It will stay in its equilibrium position. The particles themselves do not move away from their respective positions. Alright, now let me see if I can show an illustration to you. Now here you have an example of a medium. I have constructed a medium here by lining up some students. You can see if they are holding hands, one goes up and down. Look at how the energy of vibration gets transferred from one. I'm going to call each student a particle. The first particle begins to vibrate. The second particle begins a little later. And look at the profile gets generated. Now this is called a wave profile. Now what is the profile due to? The profile is due to the fact that there is a progressive phase difference between particles in vibration. Alright, I think we have been using this word phase difference quite a lot. Let's now try to understand the meaning of that. Let's now try and understand the meaning of phase of vibration and phase difference. Now here I have a particle, my basketball. If I set it into vibration, I want you to watch some of the terms I'm using. If this is the equilibrium position, it vibrates to an upper extreme. You can see that is the phase of vibration now. Back to the equilibrium, to the lower extreme, back to the equilibrium. That's one vibration. You see, each phase of vibration, the particle is at different positions. Alright, so what is the meaning of phase of vibration? Let's consider several particles oscillating between two extremes. Now here I have particles 1 and 2. Particles 1 and 2 are at the equilibrium position and they are both moving up. Now let me see if I can illustrate that here. If I have particle 1 and particle 2, they are both moving up together, back to the equilibrium, down, back to the equilibrium. We can say they are both in the same phase of vibration. So particles 1 and 2 are in the same phase of vibration because they will be always at the same positions. You see, they are in step. They are both in the same phase. There is no phase difference between them. When particle 1 is at the upper extreme, particle 2 also is the upper extreme. Particle 1 is in the equilibrium position, particle 2 is also there. There is no phase difference. While particle 3, watch the motion of particles 3 and 4. While particle 3 is beginning to move up, particle 4 has completed going up and coming back to the equilibrium position. It is now beginning to move down. Alright? I want you to understand that the phase of vibration is associated with the position. Look at this. Equilibrium position, upper extreme, equilibrium, lower extreme, back to the equilibrium. Now, remember, the time taken to vibrate completely once is called a period. Now look at these two particles now. Now, particle 1 particle 2 has gone to the upper extreme, back to the equilibrium position, and now it is beginning to move down. And particle 1 is beginning to move up. Now that means this particle in my right hand. Now when I say my right hand, it will look like the left hand to you in the picture. You see, this particle that is beginning to move down is half a period ahead of the particle that is moving up. Now what does that mean? Remember, the time taken to go up, back and down and back is one period. So this particle has gone up and come back. That means it has already covered half a period. So we can say particle 4 is half a period ahead of particle 3. When particle 3 begins to move up, particle 4 has completed half the vibration and begins to move down. I hope you got a picture of what that is. Particle 3 has to go to the upper extreme and back to catch up with particle 4. So by the time 4 would have gone down and back, they are always moving in opposite directions. Now, what is the phase difference between particles 3 and 4? You can actually, we define phase and phase difference using the angle. Now, I want you to understand the angle concept. Alright, give me a second, I will review that with you. The angle as the particle begins to move up. Remember, when it is all the way up, the angle is pi by 2 and the period is t by 4. When the particle is back at the equilibrium position, the angle is pi and the period, the time, is half of the period. When the particle goes all the way down, the angle is 3 pi by 2, you see? And what is the time in terms of the period? It is 3t over 2. And finally, when the particle is back at the equilibrium position, the angle is 2 pi and it has completed one period. Alright, I think I made more of a mess here than explaining, is that right? Now, let me try it once again. Now, if the particle is at the equilibrium, we say the angle is 0, the period t, because it hasn't started, is 0. In a quarter of a period, it reaches the upper extreme. Then the phase angle is pi by 2. In half of the period, when the period is half of the period, the phase angle becomes pi. You see that? In 3, when the particle goes down to the lower extreme, it has now completed 3/4 of a vibration. So the phase is 3t over 4, which is the same as 3 pi by 2. And when it is back to the equilibrium position, one full period is the same as the phase angle of 2 pi. So the phase difference between particles 3 and 4 is pi, because particle 4 is half a period ahead of particle 3. Alright, can you now tell me, looking at this, what is the phase difference between particles 5 and 6? 6 has just completed quarter of a vibration. The phase difference is a quarter of a period, which is the same as pi by 2, a phase angle of pi by 2. Alright, so tell me, what is the phase difference between particles 7 and 8? Particle 8 has completed what part of the vibration? It has completed 3/4 of the vibration. It is now left only the last quarter. That means its phase is 3t by 4. Is that right? 3t by 4, which is the same as 3 pi by 2. The phase difference between the two is 3 pi by 2 phase angle. In terms of the period, it will be 3t by 4. Alright, now here I have how many particles? 5 particles of a medium. Consider 5 particles of a medium oscillating with a phase difference of t by 4. What does that mean? What is the meaning that the phase difference is t by 4? It means when the first particle completes quarter of a vibration, the energy will just reach the second particle, it will begin. That is the meaning there. And when the energy reaches the third particle, the second particle would have completed quarter of a vibration. The first particle would have completed half a vibration. Alright, let's set it up like this. If the phase difference between successive particles is t by 4, remember that t by 4 means quarter of a period. As the first particle completes 1/4 of a vibration. 1/4 of a vibration means from equilibrium it will go all the way to the upper extreme. There you are. So particle 1 has now completed 1/4 of a vibration. It is now at the upper extreme. The energy will now just reach the second particle. Now look at the profile of these two particles. They are not in the same positions anymore. After another quarter of a vibration, after another quarter means after half a period. You see, this is 1/4. After another quarter, the energy is going to reach this particle. So tell me, where is the first particle now? The first particle has completed one vibration. Completed half a vibration. You see that? The second particle has done a quarter of a vibration, and the energy just reaches the third particle. And look at the profile of the three particles now. Alright, what happens after another quarter of a vibration? Now how many quarters? It is now 3/4 of a vibration. So the first particle has now completed 3/4 of a vibration. Where is it now? It is at the lower extreme. Where is the second particle? It has completed half a vibration. It is at the equilibrium position. There you are. Now where is the third particle? It has completed quarter of a vibration there. And the energy reaches the fourth particle here. And look at the profile now. Isn't that beautiful how the wave profile takes shape? What is the situation after another quarter of a period? After another quarter, particle 1 has completed one vibration. That is one period. Alright? Particle 1 has completed one vibration. Where is particle 2? It has completed 3/4 of a vibration. It is down here. Where is particle 3? It has completed half a vibration, back to the equilibrium position. Particle 4 has completed a quarter of a vibration, and the energy just reaches the fifth particle here. And look at the wave profile. And now, can you tell me, what is the state of vibrations of particles 1 and 5? Particle 1 has completed one vibration, is now ready to start the next vibration. And particle 5 has just received the energy, it is ready to start vibration. Is that right? Yes, that means particle 1 and particle 5 are going to be now in the same phase of vibration. Right? Particle 1 and particle 5 now begins to move up at the same time. That means they are in the same phase of vibration. There is no phase difference between these two particles. You can see the meaning of a progressive phase difference that creates the positions of the particles at the differences of the position that creates the wave profile. By the time particle 1 completes one vibration, look at the energy has reached the fifth particle. You see? Very important information. The distance advanced by the wave in a time of one period. You see? The time taken by the first particle to complete one vibration is one period. And what is the distance advanced by the energy during that time? Is the distance between particles 1 and 5. Now, this distance is called the wavelength of the wave. So tell me, what is the definition of wavelength? An important concept. Wavelength of the wave is the distance advanced by the wave in a time of one period. That is the definition of wavelength. Wavelength is represented by the Greek letter lambda. Lambda. Alright? So this length is the wavelength. Wavelength is represented by lambda. The distance between two nearest particles that are in the same phase of vibration is wavelength. Another definition, or the basic definition of wavelength is the distance advanced by the wave during a time of one period is wavelength. So, wavelength can also be defined as the distance between two nearest particles in the same phase of vibration. Alright, now that is the concept. Let's take a look at this particle. This particle is going to vibrate up and down, and the distance advanced by the energy or the wave during that time will be a wavelength. Now take a look at it when I run it. Now you can see the particle vibrates down, back to the equilibrium, up, back to the equilibrium. One complete vibration. The distance advanced by the wave is a wavelength. Now look at the profile of the wave. We say a wave has a crest and a trough. Now here, the particle here is at the upper extreme. The particle here is at the lower extreme. And that is the difference between the crest and the trough. Okay. Let's now obtain an equation to represent a wave. Well, the equation is going to be using the definition of the wavelength. We can now use the definition of the wavelength to get an all-important equation of the wave using the wave speed. Now, if v is the speed of the wave, how do you define speed? Speed is distance divided by time. Is that right? So speed v is distance traveled divided by time. Now just look at this. If this is the distance traveled, tell me what is the time taken for this distance? The wave advanced by this distance in what time? In one period. So if this time is one period, then this distance will be one wavelength. Is that right? The wave travels a distance of one wavelength represented by lambda in a time of one period. So in this equation, if I replace the time by one period, this distance then becomes the wavelength lambda. So we can say v, the wave speed, equal to wavelength divided by the period. You see how we obtained the wave equation. And now, look at the way I wrote it. Lambda divided by t is the same as 1 over t multiplied by lambda. Now why did I write that way? Can you give me a quantity that is equal to 1 over the period? 1 over the period is the frequency. Is that right? Reciprocal of the period is the frequency. So 1 over t equal to f, the frequency. Therefore, this is the all-important wave equation. Wave speed equal to wave frequency multiplied by the wavelength. V equal to f lambda. Now, this is true for all kinds of waves. The waves that we talk about in this lesson are mechanical waves. Waves that are generated in a medium by the vibration of the particles. This equation is also true for electromagnetic waves. See, light is an electromagnetic wave. This equation is true for all kinds of waves. And that's the reason why I said it is an all-important equation. Okay, When the particle is at the highest point, it is said to be on a crest, and at the lowest point it is on a trough. So when you talk about a full wave consists of a crest and a trough. And so wavelength can now be defined as the distance between two adjacent troughs, or the distance between two adjacent crests. You see? Tell me, what is the phase of a particle on a crest? On a crest, the particle has gone all the way up. That means it has completed a quarter of a vibration. So this particle on a crest and this particle on the next crest are in the same phase of vibration. Therefore, the distance between them is the wavelength. The distance between two adjacent crests or two adjacent troughs is also wavelength. So we have many different ways of defining wavelength. The distance between two adjacent troughs or the distance between two adjacent crests, they are both wavelength because that is the distance between two nearest particles that are in the same phase of vibration. Let's now talk about two different types of waves: transverse and longitudinal waves. What is the difference between these two types of waves? Now, if the particle vibration is at right angles to the direction of propagation of the wave, then such a wave is called a transverse wave. Now, what does that mean? I want you to look at the waves on this stretched spring. Now, you can see I'm going to pluck it. When I pluck it, the segment of the spring are going to vibrate up and down, and you can see the energy will be traveling along the length of the spring. Is that right? Look at this. All right. Now, the particle vibration is up and down. The energy is transmitted along the length of the road. You can see the particle vibration is at right angles to the direction of propagation of the wave. And this type of a wave is called a transverse wave. I have given a bigger diagram there. You can see when the free end of the stretched spring is given an upward jerk, the particles vibrate up and down. This is the particle vibration. The particle vibrates up and down, and the direction of the wave propagation. The wave is propagated at right angles, and this kind of wave is called a transverse wave. All right. On the other hand, if the particle vibration is the same as the direction of propagation of the wave, such a wave is called a longitudinal wave. A longitudinal wave. I have now a slinky stretched on the table, and you can see I'm going to set the particles of the slinky into, look at this, back and forth vibration. And I want you to watch how the energy gets transferred. Now watch when I give a forward push. What happens to each segment? Now, do you see a region where the particles are together and that region moves forward? See that? So when the particles are set in the back and forth vibration, what are produced? There are regions where the particles come together, and there are some regions where the particles are farther apart, and the energy travels along the length of the spring. That means the direction of particle vibration. The particles vibrate back and forth like this. The energy moves in the same direction. Now, this kind of a wave is called a longitudinal. Here I have that illustration. I have a slinky on the table, And if I push the slinky forward, the particles are set into back and forth vibration. So if the segments of a stretched slinky is given a brisk push forward, you will see regions where the segments are crowded and regions where they are farther apart will move along the length of the spring or the slinky. You can see the particle vibration is back and forth, and this is the particle vibration that will be back and forth or left and right, and the energy or the wave propagation is in the same direction. The energy of vibration is propagated along the slinky, forming, watch here, high density regions and low density regions. So in place of the crest in a transverse wave, what you have in a longitudinal wave is a high density region. In place of the trough, you have a low density region. So for transverse wave, you have crest and trough. For a longitudinal wave, you have high density regions and low density regions. All right, I want to see if I can show you an animation of this. Now, here is a medium that contains large amounts of particles. You can see if these particles in this region are set in back and forth vibration. If you concentrate on just one particle, you see where I'm pointing? This particle simply moves back and forth. It doesn't move away from its position, so watch it. Now, in some places particles are crowded, some other places they are farther apart. You can see high density regions form and they travel along. Low density regions form and they travel along. Now, in the same way, what is a transverse wave? In a transverse wave, the particles move up and down. The energy moves at right angles. You see? So you must distinguish between a transverse wave, you have crests and trough. In a longitudinal wave, you have high density regions and low density regions. Look at another illustration that distinguishes between a transverse wave and a longitudinal wave. Now concentrate on one particle where I'm pointing. Look at the motion of that particle. This particle is now in a crest, trough, is that right? And the crest and trough advance to the right. And look at the longitudinal wave. Concentrate on that red particle that is colored red. You can see that simply moves back and forth. When it is moving to the right, it forms a region of high density. You can see high density is moving away and low density. Regions of high density and low density move towards the medium. The particles simply vibrate back and forth. I want you to understand, when a particle moves to the right, if it is in a region of high density, when it moves to the left, it is in a region of low density. So try and distinguish between a transverse wave, which generates crests and trough, and longitudinal waves that creates high density regions and low density regions. We will now obtain a mathematical equation for the speed of transverse vibrations of a stretched string. What is the meaning, the speed of transverse vibrations of a stretched string? If I have a string stretched like this, if I set it into vibration by plucking it one end, by creating a transverse vibration, what is the speed with which the energy gets transmitted along the string? Now, when a stretched string is plucked, the transverse vibrations so produced are propagated through the length of the string like this. You have a stretched string and I pluck it at one end or create a pulse, the pulse will move along the length of the string, and we will look at the speed of propagation. The speed of propagation depends on what factors? There are two main factors on which the speed will depend. I want you to understand both these. It will depend on the mass per unit length. Mass per unit length. In other words, it indicates how thick the wire is. If the mass per unit length is large, it will be a thick wire. And if the mass per unit length is small, it will be a thin wire. Alright, can you make a guess? Which of the wire is more efficient in transmitting energy through it? Or in which of these mediums will the energy travel faster? A thick wire, a thick string, or a thin string? I'm going to leave it for you to think about it. Okay, now what we're going to do is we're going to take a small segment of the string of length I'm going to call delta S. You see, I have just created a pulse. Now this is the pulse of length delta S. Consider a pulse of length delta S and radius r. In other words, this delta S is actually part of a circle, and the radius of that circle is this r. T is the tension on the string. What is the meaning of T is the tension? Well, it means the force of stretch. The force of tension is the force of stretch. And mu is the mass per unit length. Well, actually, in the last slide, I forgot to tell you that the speed also depends on how taut the wire is, how strongly the wire is stretched. Okay, so T is the tension. Now this is the tension force represented by the arrow. This is the tension force. That is, you can see when the wire is stretched upward, these tension forces try to pull the wire back. Is that right? So this is the tension force, and that is the tension force on either side. When the pulse is in the form of an arc of a circle, it experiences a centripetal acceleration. You see, the tension force is actually a centripetal force, and it pulls the segment back. It experiences a centripetal acceleration, which is supplied by the vertical components of the tension force. You see, this tension does two things. This tension pulls the wire sideways and also pulls this segment downward. The acceleration, the centripetal acceleration, is provided by the component of this tension that is downward. So, first of all, let's mark the components of the force. Now, this tension has a downward component which is T sine theta by 2. If you know some geometry, now this is our segment of length delta S. The angle it subtends at the center is theta. If you now draw a tangent to that segment, the angle it will make with that tension force, which is tangent to that, will be half of this angle. That's a geometry lesson. So if this angle is half of theta, then this component will be T sine theta by 2, and the component that stretches the string, pull the string to the left, will be T cos theta by 2. I hope you understand. We did a lot of these in physics 1. This tension force T has a component T sine theta by 2, try to pull it down, and T cos theta by 2, trying to pull it to the left. Similarly, there is a T sine theta by 2 on the right and a T cos theta by 2. Now if you notice, these two are opposite to each other, they cancel. This T cos theta by 2 will cancel with this T cos theta by 2. That means the only two surviving components are the t sine theta by 2. The vertical component of t on each side is t sine theta by 2, where theta is the angle subtended by this pulse at the center. Now, the total centripetal force, remember, it is the component of the force pulling the delta S down that provides the centripetal force. So what is the total centripetal force? It is this plus this. That will be 2t sine theta by 2. I hope you understand. It is the sum of these two vertical components that gives the centripetal force. So the total centripetal force is 2t sine theta by 2. Do you remember the equation for centripetal force? If an object of mass m moves with a speed v along a circle, what is the measure of the centripetal force? I will come back and ask you that again. Now here I'm going to take a small approximation. When the angle theta is very small, sine theta by 2 can be approximated as theta by 2. You remember we did this in our first lesson also. When the angle is small, sine of an angle is approximately equal to angle itself. Remember, the angle is measured in radians. So we will replace the sine theta by 2 by theta by 2. That means the centripetal force now is 2t multiplied by theta by 2. What is 2t multiplied by theta by 2? That will be t theta. The 2's will cancel. Now, well, I had asked you this question. The centripetal force on an object of mass m moving with a speed v in a circle of radius r is mv squared over r. I hope you remember that equation. So what we're going to do is we take this quantity and equate it to this. Alright? So what is m here? M is the mass of that string. You see? And you know, the delta S is the length of that string. Its mass per unit length is mu. You remember we call it mu, the Greek letter, mass per unit length. If you multiply the length of the string with mass per unit length, you will get the total mass of the string. So mass of the string m equal to mu times delta S. Where what does mu stands for? Mu is the mass per unit length. So mass per unit length multiplied by the length will give you the mass. And theta, well, you know, I have actually used many results here which I expect you to know. The arc of a circle, delta S is the arc of a circle. And the length of the arc will be radius multiplied by the angle theta. You see, this result is very important for you. The arc of a circle subtending an angle theta at the center, this is delta S. This is the radius r. So we get delta S equal to r times theta. Therefore, theta equal to delta S divided by r. So we're going to say theta equal to delta S divided by r. And let's use all those in there and form the equation. That gives me mv squared over r equal to t theta. And I'm going to replace my m by what? M equal to mu times delta S times v squared over r equal to t times theta. And what is theta equal to? Theta equal to delta S divided by r. Now look at the beauty of this relation. R on the right and R on the left will cancel. Delta S and delta S will cancel from both sides. That gives me v squared equal to t divided by mu. Right? After cancelling delta S over R from both sides and dividing by mu, I get V squared equal to T divided by mu, or V equal to square root of T over mu, where T is the tension, the force stretching the string, and mu is the mass per unit length of the string. A very important relation. Speed of transverse wave on a stretched string is given by V equal to square root of T over mu. Don't forget that. Let's now talk about energy transmitted by waves on a string. The vibrations of a stretched string can be compared to the simple harmonic vibrations of the loaded spring. A segment of the string vibrating is exactly the same as the simple harmonic vibrations of the string, of the loaded spring. Alright, tell me, what is the total energy of vibration of this? What is the total energy of vibration? You remember the equation? Equal to 1/2 Ka squared. Now, the energy of vibration of a loaded spring is 1/2 Ka squared, where, I hope you remember these, K equal to M omega squared. You remember that one? Well, the first time I introduced this, you know that omega equal to square root of K over M. Therefore, K equal to M omega squared. If you square both sides, is that right? We get omega squared equal to K over M, or K equal to M omega squared. So, we will now use energy of a vibrating segment of string. In place of K, we will use M omega squared. If mu is the mass per unit length of the string and delta x is the length of the vibrating string, then K equal to M omega squared. What will M become? If mu is the mass per unit length and delta x is the length of the string, then mass M will be mu multiplied by delta x. You see, K equal to M omega squared mu delta x omega squared. And therefore, the energy delta E of this vibrating piece of string can now be written as delta E equal to, remember we're using the same equation, 1/2 Ka squared, where K is mu delta x omega squared. So that will be 1/2 K. K is mu omega squared delta x. Watch, I have rearranged it slightly. Mu omega squared delta x stands for K, and Ka squared now become mu omega squared A squared delta x. And that is the expression for the energy of vibration of a stretched string. Now, delta x, the length of the string, equal to V times delta t. Is that right? Where V is the speed. Speed multiplied by the time will give you the distance. So I'm going to replace this delta x by V multiplied by delta t. And what does the equation now become? Delta E equal to 1/2 mu omega squared A squared V delta t. Delta x is replaced by V delta t. Well, power P transmitted by the wave is the rate at which energy is transmitted. In other words, if I divide this delta E by this delta T, delta E by delta T is the rate at which energy is transmitted. That will give me a measure of the power transmitted. Power transmitted is delta E divided by delta T, which is 1/2 mu omega squared A squared V. A very important relation. the energy transmitted by a vibrating string is 1/2 mu omega squared a squared v delta t, where mu is the mass per unit length, omega is the linear frequency, the omega equal to 2 pi f. Is that right? Okay. Power transmitted is 1/2 mu omega squared a squared v. Again, mu is the mass per unit length. Omega is the angular frequency, which is 2 pi f. A is the amplitude of vibration, and v is the speed of energy transfer. Well, we will use the results we obtained in this lesson to solve problems in the second part of this lesson. So this lesson I'm going to call 1.2a, and then examples, worked examples will be 1.2b. Now in the meantime, I would like you to go back and look through this lesson one more time and learn all the basic core concepts. Alright, I will see you for the problem solving session a little later.